Good afternoon, everyone. On behalf of Partners in Project Green, I would like to welcome you to our monthly series of green technology webinars. For those of you who might not know, Partners in Project Green, developed in partnership with Toronto and Region Conservation and the Greater Toronto Airports Authority, is a growing community of businesses working together to green their bottom line by creating an internationally recognized eco-business zone around Toronto Pearson. Before we start the webinar, I would like to run through a few logistical items. Note that your lines have been muted to avoid background noise. If you have a question during the presentation, you can click on Raise Your Hand within the small vertical control panel, and I will unmute you. You will have to enter that a PIN that was provided to you for me to unmute you successfully. But if that doesn't work, we can always use the chat section to get your questions. So if you have come across any issues throughout the webinar, please send me a direct message by clicking on my name to start a chat. Let's begin. This month's Green Technology webinar is focused on power factor. We are very fortunate to have Don McQueen joining us this afternoon to give us some tools and opportunities to improve the power factor at our facilities. Don has over 35 years of experience in the electrical industry and is among Ontario's top power factor correction experts. In 2001, Don founded Power Factor Services Limited, which focuses entirely on power factor correction, power quality monitoring, harmonic load studies, and power quality investigation. Don has presented numerous speeches on power factor correction and power quality monitoring, and regularly holds speaking events. So he continues to provide power factor correction services and power quality monitoring through Power Factor Services Limited, helping clients reduce their electrical utility costs and maximize efficiency of their power systems. So you can take it on now, Don.
Good afternoon, everybody. Again, my name is Don McQueen. I think you can all perhaps see on, or should be able to see on the screen, what is power factor. Power factor basically is a percentage. It's a ratio between the amount of real energy to do the work, which is in kilowatts, compared to the total amount of power that you're using from the utility, which is kVA. Typically, utilities actually measure in kilowatts as well as kVAR. kVAR being inductive reactance. We're going to get a little more further into it, but just to give you some idea of what things are that have good power factors. Incandescent lights typically have a unity power factor. As we get down into motors typically have a power factor of somewhere in the 80s to the high 80s. With in motors less than, say, 300 horsepower. And that would be at full load. As a motor is doing less work, the power factor actually decreases. For example, a 10 horsepower motor would typically have a power factor of about 83, 85% at full load. But at half load, the power factor would be down likely into the mid-60s. And if it's a quarter loaded, 25%, the power factor could be down well into the 40s power factor. So if you take a number of these different motors in a facility, that could be industrial or commercial, and you start adding up low power factor motors that are lightly loaded, you end up at your facility with a power factor of likely less than 90%. A number of other things that require magnetizing energy, which is kVARs. I said motors, transformers, also they set up a field, so there's VARs required for transformers. DC drives typically have a very low power factor, generally in the 60s. Lighting ballasts, depending on the make, the newer lighting ballasts, electronic, typically have a very high power factor. And variable frequency drives now have improved over the years, and they also have a relatively higher power factor. So what is it that what do we use power factor for, or power factor correction for? Generally, and this would be probably 99% of the time, 95% of the time, power factor correction is used to reduce the hydro demand savings on the hydro bill. We'll get to what the percentages are, but basically in Ontario here, sites pay power factor penalties on power factors less than 90%, except in Toronto, and Toronto has a different rate structure, and it is billed on kilowatts separately from kVA, so Toronto actually has a unity power factor. Another reason why we put capacitors on is to decrease loads on transformers and related equipment. We'll get to that a little later in the presentation. And along with the decreased load on transformers, motors, etc., there's also some decreased heating losses in the cables feeding the motors. One of the things that's happened over the years is we've been called out to sites, and people will say, we're interested in putting in power factor correction. We go, we have a look at the site, and in some cases they actually have capacitors. Sometimes the customer doesn't even know they exist or they've had them. And in some cases they're turned on, and in some cases they're turned off. So anybody in the maintenance end, they come in many, many different sizes and colors, as you can see here. We have, you can see the cursor, we have 3, I think these are about 50 or 60 kVAR fixed capacitors mounted up on a wall above some disconnect switches. And over on the right side here, we have a site that has a disconnect switch actually up in the ceiling space. I'm losing my mouse here, sorry. And we have a capacitor bank mounted high up. And these are cases where, as plants change with maintenance managers, et cetera, over the years, and even in some commercial sites, people forget that they even have them. We also have, there's some pictures of some failed capacitors. Capacitor banks sometimes carry a negative note to them where people have had some problems, and these sometimes, or a lot of times actually, are due to harmonic currents. And again, we'll get into that a little later. So these are a couple of, I'd say, catastrophic failures. The one on the right here, actually it's the section on the right side of this automatic bank that had actually failed, and there was a fire involved in that. Here's a couple of good-looking capacitor banks. These are both automatic capacitor banks, and as we'll get to a little later, this is a conventional capacitor bank on the left. We have our fuses, we have some inrush current limiters, we have the contactors and the individual capacitor cells. So this particular bank will step in and out as required to maintain whatever target power factor that one is set for. The one on the right here is a harmonically filtered capacitor bank, which is becoming more and more of a requirement these days, with more harmonic loads being added to plants, such as AC variable frequency drives. It's probably one of the largest contributors of harmonics nowadays. DC drives, of course, have very high harmonic, as well as rectifiers. But here we have a similar capacitor bank. We have our fuses for the individual steps. We have our contactors, and these small transformers, are actually tuning reactors, and they actually limit the amount of harmonics that a capacitor bank will actually absorb if you have harmonics in your site. Now we're just going to get back here to, we're talking about kVARs, or inductive kVARs. This goes back to Pythagoras' theorem for the calculations here, but normally, in most cases, capacitors are installed at the main switchboard in a facility, typically today. So an example of how we do some of the hydro bill savings, we look at a plant here, and on the left-hand side, we have a facility that's using 800 kilowatts of power to run their system. and their kVA is actually 1,000 kVA. So if we take the 800 and divide that by 1,000, we end up with an 80% power factor. Now, to get our 1,000 kVA, this particular site is actually using 600 kVARs of inductive reactance. That would be the magnetizing power required to turn a motor, make a transformer operate, and etc. So in this particular site, just to give you an idea of what happens for our kVA, we have actually added on the right-hand side here, we've added 300 kVAR of capacitance to this site. So the 300 kVAR of capacitance basically negates the 300 kVAR of inductance. So we find that our triangle here has now been reduced, and the calculation for kVA is the kilowatts squared plus the kVAR squared, and the square root of those two values is in fact a kVA. So if you had a 1,000 kVA transformer, excuse me, feeding your site, the transformer, and you had a load of 1,000 kVA, your transformer would be running quite hot. You also could end up possibly perhaps blowing some of the main fuses in the site periodically. By adding capacitors, we actually can reduce the load on the transformer. I'm going to go to the next here to give you an example of what happens. We're going to look at this as being a 100 amp load, which is the top here on the right, and we have a hydrometer on our left. So if we were to take a simple amp meter, I'm sure hopefully everybody has seen one. Normally I do these things with an audience, and I can actually hold up pieces of equipment. However, if we take a 100 amp load, and this could be a motor, one large motor or a number of different pieces of equipment. If we take a simple amp meter and we put an amp meter down by the motor, it would read about 100 amps. And if we took one up by the hydrometer, it would be about 100 amps. And if we equate at 600 volts, 100 amps to be approximately 100 kVA, it's a fairly close number. The hydrometer would be registering 100 kVA, and as it's alternating current, it registers it 60 times a second, back and forth. So if you were to look at a hydro bill at this particular site here, the kVA demand would be 100, and the kilowatts would actually be 80. And so if we take a capacitor bank, and in this particular case, if we added, it's highlighted here, a 60 kVAR capacitor bank, and we added that to some portion in the facility, and if we use a motor as an example, if we added 60 kVAR, and we took our our amp meter, and we connected it between the load over here, being perhaps a 100 horsepower motor, and between where the capacitor bank was connected, we would read 100 amps on our amp meter. Now, if we move the meter up between wherever the capacitor bank was connected and the hydrometer, our amp meter would actually read about 80 amps. So now, the hydrometer has a lower demand rate. In this particular case, it would be 80 kVA and 80 kilowatts, resulting in a unity power factor. And one of the reasons that the utilities charge a demand charge is basically to, say, recover or look after the cost of actually generating a demand amount of power. Demand being you as a facility, the utility will supply you whatever number of kVA or kilowatts that you require as you demand. So in cases of hydro bills, your hydro bill would be based on consumption, which is the total amount of energy that you've used in a case of 1 month period, plus a billing demand, which is the highest amount of kilowatts or kVA that you have used over a 15-minute window. The next slide here is it shows the two parts of a hydro bill: the energy, which is kilowatt hours, and the kilowatt demand. Now, we're talking about Ontario here, so in all areas other than Toronto, the kilowatt demand that you pay in your hydro bill is based on 100% of kilowatts or 90% of kVA, whichever is greater. And this is typically a demand on either a 15-minute or a 1-hour sliding window. So if you think that if you start two large compressors within a minute or so of each other, it's really not going to affect your peak demand for a month, because it's actually averaging over 15-minute period. So whether you turned on two 100 horsepower compressors within a minute of each other or within 3 minutes of each other, the overall peak inrush current that a compressor would draw would not be seen on your demand component of your hydro bill. Toronto Hydro, as I mentioned, has a slightly different billing method, and they, since 2001, I believe, or 2000, they now bill on a kilowatt and a separate kVA charge. So whereas in Mississauga, for instance, with a 100% kilowatt and 90% kVA, if your power factor is at 95%, there is no recovery of any demand charges with a 95% power factor. However, in Toronto, because it's a separate kilowatt and kVA, there is a power penalty recovery basically right up to 100%. Although keep in mind that the closer you get to unity or 100%, the more kVAR you require to move 1%. So in Toronto, as an example, we typically look at targeting somewhere between 95 and maybe 97% power factor, as the cost of going from 97 to 98% power factor typically is not worth the extra dollars. We have just down right here, I've highlighted in yellow that VA or kVA is volt amps, and watts is the volts times the amps times the power factor. And say we'll get to that something later in the presentation. This is a sample hydro bill. This one is actually from Brampton Hydro 1. Most of the utilities now are actually showing the power factor on the hydro bill. Sometimes it needs to be calculated, but they typically now show you the values that you require. In this particular case, we have the power factor is highlighted with an 81.75%. And if you were to take the kilowatt demand of 1425.60 and divide that by kVA of 1743, you would get a power factor of 81%. So in this particular case, our power factor is less than 90%. So the utility will take the measured kVA, which is 1743, and they will take 90% of that. So if we look up into this area here, where we see a demand of 1,569 kilowatts, that basically is 90% of the peak kVA. So in a case like this, to reduce or to increase our power factor to 90%, we would have to put in enough capacitance so that 90% of our kVA equaled to greater or less than 1,425 kilowatts. next slide here will give you a better example of, sorry, the next slide here is Toronto. I'm jumping around a bit. Toronto, as I mentioned, is at Unity. So they have, the first highlighted here is the KVA, and that's, in this particular site, it's a large user, so it's just a little over $4 plus some additional charges that they have. And the kilowatt is $31.44. So if you were to take that kilowatt here at $31.44 divided by 39.59, you would end up with the power factor, which I think in this case is around in the 70s, yeah, around the 70% power factor. So we're going to go back to the first example, which would be EnerSource, Brampton Hydro One, PowerStream, all the other utilities in Ontario other than Toronto. This is a typical billing table that we would do where we look at the past 12 months hydro bills to determine what the potential savings are, what the power factor is, etc. In this particular case, they say we are at less than 90%. I'm going to just try this highlighter here. We're less than 90%, so in this particular case, our power factor is 80. On that particular month, we're paying $767 in penalties, and to eliminate those penalties, that particular month would need 473 kVAR. Now you'll notice that each month the amount of kVAR changes. Same thing with the penalties, and a lot of that has to do with the demand over a period of a month from the site. So in some cases, in this particular case, one would require 358 kVAR to eliminate $11,744 in annual power factor penalties. Typically, before we go into a site to determine exactly what the firm cost would be, we would look at harmonics, harmonic levels in a site, which would determine whether we can use a conventional capacitor bank, non-filtered, or a harmonic filtered bank. And we use a couple of different numbers here. These are simple numbers. They certainly do range, but a conventional capacitor bank, if we looked at it to say, well, somewhere between $55 and $75 per kVAR, and the harmonic filter somewhere between $75 and $95 per kVAR. And this is an installed range of dollars. You find here, if we had installed 300, and I'm going to use my highlighter for a moment. If we installed a full 358 kVAR, there would be annual savings of over $11,000. And we have a couple of different paybacks here. So for instance, if we required a harmonic filter and there were some existing disconnects that we could use, we may be able to get into this area here. Now, a lot of times paybacks become very critical for companies, and companies range anywhere from 1 to 3, and some municipalities actually go as high as 8 years, which is pretty easy to do. But in a case like this, if a site had a 2-year payback or less, then rather than putting in 358 kVAR, which they really only needed for 1 month, right up in here, if they put in, say, 250 kVAR, they would basically be utilizing that 250 kVAR most every month. And they would end up with an average power factor of about 88%, and their annual savings would be around $9,900. So it's basically a little less than 100 kVAR, but they can get their payback down to 1.9%, as low as that with a harmonic filter, and as low as over here about 1.4 years with a conventional bank. We go on to the next slide. This is for Toronto Hydro, which is at Unity, and here the same thing would apply. To be able to correct or to get to Unity, you'd need a minimum of 891 kVAR to save about just over $18,000. As I mentioned before, correcting to Unity is a relatively expensive thing to do. So the bottom table down here, we can see that we have 600 kVAR would give them an average of 97% power factor with about $17,000 annual savings. And if we went down as low as 300 kVAR installed, they'd have an average power factor of a little less than 90%. Still be $10,000 in annual savings. Sorry, 10,000 annual savings, and these are the associated paybacks. So again, if somebody had a maximum 3-year payback, they could be looking at, if it was a high-cost filter and it required disconnect switches or more cable because it was further away from the main switchboard, they may want to go with less than 400 down to 400 kVAR or so. One of the things, the next thing we're going to get at is what we've looked at right here is primarily demand savings, which is the demand component of the hydro bill. There are some associated savings that one sees by putting in capacitors, and that is I squared R losses. I squared R losses is the amount of energy that's used to transfer amps or current through cables, wires, bus duct from the main metering point to the end load. If you were to put a capacitor bank on at a main switchboard, and let's say it was about physically 10 feet from where the hydrometer would be, and you were able to reduce your load from 1,000 amps down to 800 amps, there would be very little in the way of heat recovery because the distance is relatively short. Now, if we take that same scenario and we move the 800 kilowatts of load further out into the plant, the I squared R losses, of course, are much greater, and there can be some additional kilowatt-hour savings that capacitors can recover. As I mentioned earlier in one of the slides, I'm just going to jump back here, back over to this particular decreased demand load. This sometimes is used with on sub-services, both in commercial and in industrial, where you may have a splitter or a secondary panel, maybe 500 feet or more from the main switchboard. And if we use this 100 amp load as an example, if this was a 100 amp panel with 100 amps on it, you sometimes could blow the fuses to that. The other thing is the cables. If you were to take your hand and put it around the conduit of the cables feeding that, it would actually probably be almost too hot to hold your hand on for more than 30 seconds or so. So in cases where you have a long feeder, you can actually put power factor correction on to improve the power factor up well into the 90s, and you can actually reduce the amps. So if the capacitor bank here is actually installed, we move this right down to the end load, you could have actually reduced this 100 amp load right down to 80 amps. and the reduction of that 20 amps through the cable, the heat loss associated with that 20 amps is what can also be recovered in kilowatt hours with the addition of power factor correction.
So, Don, if I can just interrupt you for a quick second, we do have a question from Paul. What happens if you include new electrical generation, like distributed energy, within the facility or campus internal grid?
Sorry, could you say that again?
What happens if you include new electrical generation, in brackets, distributed energy, and bracket, within the facility or campus internal grid?
Could you perhaps unmute that caller?
Yes, I will.
I may be getting to answer that question, but can he ask that?
Sure. I will try to unmute Paul. Paul, you should be unmuted right now.
Hi, Paul.
No, I don't think his voice is.
I'll have to assume.
He may not have a mic, so.
Okay, that the distributed energy through a facility would be what we're basically talking about, which is reducing load and the I squared R losses throughout a facility. If you're referring to generators, capacitors, power factor correction, and generators are not used a lot. There's issues with a leading power factor and generators with respect to voltage control. If anybody has any questions to that, they could actually just go to powerfactorservices.ca and send me a note, and I could explain a little more on power factor correction with generators. I'm sorry if that didn't answer your question very well, but in any case, this may help a little bit in this particular one right here.
He has indicated that yes, I think it has been answered, so I think we're okay with that.
Okay. This is an example right here. The I squared R losses uncorrected is an example that was done years ago. This is a 240 volt system, single phase, but just to give an idea of what the I squared R losses could be. In a case like this, we have a 5 horsepower motor, and right up in this area here, if we go back to our original power factor being the kilowatts divided by the kVA, we have a power factor of 70. We're actually using a total of 21.95 amps if you were to take a meter on that. And if we broke out those amps between the kilowatt amps, if we could call it that, and the kVAR amps, magnetizing energy, these are the two values. So if you actually took if you squared these two values here, took the square root of that, you would end up with 21.95 amps. So in this particular case, we have a motor which would be drawing 3.73 kilowatts right here. That would be if the motor, well, let's say, was right next to the hydrometer. Now, if we took that motor and we moved it, in this case, I think it was actually 250 feet away. I think this says 1,000, but I don't think that was the case. It's about 250 feet away. That right there, yes, 250 feet. It's a number 10 wire, so it would be about 2/3 loaded. If we moved that 250 feet away, we would actually have some line losses right here of about 1.2 kilowatts. So if the motor was at the main switchboard, we would be registering 3.73 kilowatts on your hydrometer. If we moved it out 250 feet, you would actually be measuring 3.85 kilowatts. If we look at this, it amounts to about 3.1% in losses, which if this motor was running for a month, it would be about $4 in losses for that particular motor. on the next slide here, what we've done is they've added some kVAR. So our power factor has now gone up to 91%. You'll notice that our kilowatts are still at 3.73, and our kVA has been dropped down to 4.1. So we now have got similar case. We have our work being done here, which is 3.7. That would be regardless of where. But we now have reduced our losses from 0.14, which we had in the previous slide, to 0.073. That's because we've reduced our current from 21 in the previous to 17. So in the calculations that they've used here, it's 0.047 kilowatt, which is pretty low when you think about 47 watts. But if we look at percentages, it's about a 1.2% recovery on a 12% current reduction, and that would amount to about $1.60 in monthly savings. So there are actual savings that can be done, kilowatt savings. I'm going to show you a little later. These things are sometimes very, very difficult to see on a hydro bill. You certainly can see the kilowatt, the kVA reduction because it's in amps or kVA, but the kilowatt reduction would be very difficult to see the difference on a hydro bill over a period of a month. Any case, we're on to the next slide. This is I have a little beware up here. This was something that a customer had sent to me on some company that had been selling a capacitor bank, and this would be distributed throughout the facility, much like we had on the previous slide, except in this particular one, we have, this is measured in amps to before. We have an average of 266 amps that they have got with a power factor of 88%. They put in some capacitors, and the current dropped down to 223 amps with a power factor of 99, which one would expect that to happen. The problem was that they were basing their savings on volt amps, or kVA, and not watts or kilowatts. So the calculation that they have was a base, this is our 266 amps highlighted in yellow here, times for three-phase. And you'll notice up here with the watts, voltage times amps times the root of 3 divided by 1,000 is kilowatts, they didn't show the power factor in there. So consequently, they've calculated out that this particular load would cost over $177,000 a year. And if they were to put in a capacitor bank, they would reduce their annual cost down to $148, which would be about a $28,000 savings. Now, as we get on to the next slide, what I've done is I've taken the same values that they have used, and I've actually put the power factor in that they had. So the value, or the original value of $177,000 cost, it really would have only been $156,000. Their savings after the kVAR, I think they had 148, calculated about 147,000. So in a case like this, at very best, the savings could be as much as $9,000. Now, this is about 6% of the total kilowatt. The 6% in I squared R savings is, I've heard the number used a number of times. It is it's a fairly large percentage. It's unlikely to happen unless you have heavily loaded cables at great distances. In any case, I said about the 6 kilowatts would be the very best that one could do on that. I've done a little example here on the recovery or the potential kilowatt recovery of installing 100 kVAR. This would be a site. I think I'll use the highlighter because I'll be on this one for a couple of minutes. We have a site here that has 500 kilowatt or 500 kVA demand there with a 400 kilowatt demand. We have a power factor of 80%, and we're looking for a 50 kVA reduction, which would take their kVA down to 450, which would give them a 90% power factor. If we look at some potential kilowatt I²R loss recovery of 10% of the reduced kVA, and we're looking at 50, we could actually get down to about a 1% overall reduction in kilowatt hours. That's a possibility. So if we look at our 100, we need 100 kVAR over here to be able to reduce our kVA by 50. So if we were to take that 100 kVAR and distribute it throughout the plant, and we're talking about putting it on motors that are at least 250 feet away from the main switchboard or the main hydrometer, we could look at a possibly 4 kilowatts per hour recovery. So if we take a plant that operates 5 days a week and 16 hours a day, we end up with about 336 hours per month. Now, if we had some our kilowatt reduction per month, we took 4 kilowatts per hour times the 336, we could end up with as much as 1,344 kilowatt hours per month in I²R losses. In a case like this, regardless of whether you put the capacitors at the main switchboard or if you distributed it out into the facility, you still would see about a $350 monthly reduction in your on the demand charges at $7 per kVA or per kilowatt demand. Our monthly kilowatt recovery, if we're using 10 cents a kilowatt hour, in this particular scenario would add about $134 a month in savings. So if we roughly look at a ballpark cost of installing 100 kVAR fixed at a main switchboard, the cost would be about $6,000. And if we were to look at an annual recovery of the demand charges, we would be looking at an annual reduction of about $4,200, which would be a very, very good payback, of course, on 100 kVAR. Now, if we took 13 7.5 or 7.5 kVAR capacitors and we installed them on 13 25 horsepower motors, again, that were a minimum of 250 feet from the main switchboard, and generally on smaller cables, so that they were at least 2/3 loaded. We could see potentially the I²R loss recovery, as I said, of $134 a month. So if we looked at the combination of $350 per month in demand charges plus $134 in I²R losses, we would end up with annual savings of $5,800 over the $4,200 installing the capacitor banks at the main. So if we use, in this particular case, it's about a 1.6% reduction in kilowatt hours, and this was based on another site that actually used about 83,000 kilowatt hours. So it's about a 1.6% reduction in kilowatt hours. Now, the main question that one would have, or at least I have, is whether you could actually see 83,000 kilowatt hours if you could see a 1.6% reduction If you look at your hydro bills over a year, you're going to find that the kilowatt hours range greatly from month to month. And trying to say, yes, I have saved 1.6% or 1.3% or 0.8% in kilowatt hours, it's really more of a calculation, and it's not really a measurable value. Whereas the kilowatt or kVA demand reduction from your hydro bill is very easy to see because your kVA actually reduces and your power factor increases on that. Now, that being said, the next slide here is kilowatt conventional capacitors. So we showed you earlier in the presentation a capacitor, fixed capacitor banks that were up on the wall, and we also had some automatic banks. Typically, to keep the cost down, we generally look at on both commercial and industrial of installing somewhere between 10 and 15% kVAR to the transformer kVA size. 15% kVAR to kVA, unless we use 150 kVAR on a 1,000 kVA transformer, would equate to about a 1%, a little less, 0.85% voltage rise during no load or, let's say, weekend conditions. So on a 600 volt system, if your voltage was 600 volts, you could actually see somewhere around maybe 605, 604 volts with fixed capacitor. The issue sometimes is on the weekends, utility voltages go up, and your 620 volts on the weekend could end up being 625 volts or 624 volts. So anything more than 10 to 15% of the kVA of the transformer, we would use either an automatic switch bank that you saw earlier. There's some pictures of that. Sometimes we will use a combination of a fixed bank and some automatically switched capacitors. We could even talk about the early example of putting capacitors on motors, 25 horse or 50 horsepower motors, where the capacitors would come on when the motors came on and would be turned off when the motors were turned off. In the end, it really comes down to payback of the overall system. In some cases, if you were to put in say if we had a 1,000 kVA transformer, and the decision between whether you put in 100 kVAR fixed or 100 kVAR automatic, you probably would be looking at maybe a 2-year payback with a fixed bank, and probably in that size about a 4-year payback with an automatic. So you effectively would be saving the same amount of money. You just would be paying more money for your capacitor bank. I think we're getting closer to the end. I'll try and speed this up a bit. This is on the left-hand side over here. We have a utility capacitor switching event. Utility switch capacitors on, high voltage capacitors on and off to reduce the current, just like we showed earlier that we could reduce the current on a line by putting capacitors. They do the same, and they reduce the current on their transmission lines, which also results in a voltage increase. So they do it on a combination of reducing the current on their lines and increasing the voltage when required, particularly in the summertime when the air conditioning is loaded. This particular one is a small. You can see a switching. There's a zero drop. The voltage in here drops as the capacitance is switched on. Now, this would be typically what you would see in a facility if you either did not have any capacitors or if you had a harmonically filtered capacitor bank. One of the problems that we see with conventional capacitors is the utility switching capacitors sometimes will resonate or interact with capacitors in facilities. So here, this is the voltage here. We see a very, very high momentary voltage rise and ring wave. And this is basically a resonance between the utility and internal capacitors in a facility. This is not only just in power factor correction capacitors. This also could be literally in variable small capacitors and variable frequency drives, computers, anything that has a small capacitor in it. The bottom here is the current, and although it's very momentary, you can see here where this is a peak current. Basically went from a little over 2,000 amps peak over 4,000 amps peak. Some cases where you have variable frequency drives, they actually you can have some nuisance tripping where they will trip offline in cases like this. So utilizing a harmonic filtered capacitor bank, the result would be something more like on this side here. Now, in saying this, one of the reasons why we look at the harmonics when we go into a facility is if you do have harmonics within your facility, if we go back to the I squared R savings and we're using distributed capacitance throughout a system, we could end up with having to basically filter all the capacitors in a facility. So when we go into a facility to look at installing capacitors, we look at the facility. If they don't require harmonic filters, we generally recommend the use of a harmonic rated capacitor bank, which has a much higher voltage rating than a conventional capacitor bank. And these, call them filter-ready capacitors, high harmonic capacitors, can be upgraded later into a harmonic filter. So installing, let's say, for instance, 100 kVAR at the main switchboard, if over 2 years somebody was put in a capacitor bank, and then afterwards drives were put in and there was some nuisance tripping, a 100 kVAR could be fixed or could be tuned with a tuning reactor and upgraded to a harmonic filter at a relatively low cost. If we were to look at distributed capacitors, we go back to having capacitor banks on all of our motors. We now are faced with applying a tuning reactor to all of those capacitors out in the plant. So now the cost of filtering becomes very large. As I show in this particular slide here, harmonic filters are 2 times the cost of a conventional, and that price basically varies depending on the size. Converting a 100 kVAR capacitor bank to being filtered would cost probably about would probably cost slightly more than adding a tuning reactor to a motor that only required 25 kVAR. Being that a 25 kVAR tuning reactor is certainly not, it would be a half to 50% of a 100 kVAR tuning reactor. So once we get into distributed capacitance throughout a facility, as long as we are not going to have any harmonic issues down the road, it's probably the best way to go. The I squared R loss recovery makes a lot of sense. But these days, with more and more variable frequency drives, new DC drives, etc., the requirement for filtered banks is becoming greater and greater. Now, one of the things that we need to think about is the amount of kVAR. And if you have capacitors put in and they say, yeah, you need 100 kVAR, and then you notice on your power factor, on your hydro bill, you're supposed to be at 9 90 and you're only hitting 88.9 or 89.1, it could have to do with the voltages in your facility. Typically, kVARs are rated in Ontario here at 600 volts. So at 600 volts, 130 kVAR would actually deliver, 100 kVAR, 130 kVAR will deliver, 136 kVAR at 615 volts and 119 kVAR at 575. So typically what happens is when you're at your peak load in your facility, that's typically when you need the most kVAR for correction, and that's also when your voltage is likely going to be at its lowest. So every site needs to be looked at individually to determine how many kVAR you need to go over a little more or less. This next slide here is just basically, this again shows you what size capacitors that you can put on breakers or disconnects. Typically in the electrical code, both for Canada and the U.S., they basically are sized at 135%. We have found that if you size the disconnects and the wire for 135%, fixed capacitors in particular are on all the time, and they actually get quite warm at 135%. We typically recommend 150% for both disconnect and the breakers as well as the wire size. And this table down here just gives you an example of putting on we can put 40 kVAR on a 60 amp disconnect. A 200 amp disconnect is a good example because we would recommend 135 kVAR, and whereas the code allows you to put in 150. And if you put 150 kVAR on a 200 amp disconnect at 600 volts, you actually would find the conduit was actually warm to the touch, and in some cases you're actually increasing some of your I2R losses. I haven't heard any questions at all. I'll just end this if there's any other questions. My name is Don McQueen, Power Factor. We specialize in capacitors, sales, service, installations. We do a lot of load disturbance monitoring, power quality investigations, and IEEE 519 compliance, which is more for newer sites for engineering companies, which is typically in the specifications.
Sorry. We do have one question for you, Don. So you have convinced Paul that there are cost savings to making sure line losses and other demand-induced deficiencies are dealt with. Are there any other issues regarding power quality, especially if one's campus includes computer farms such as ISP server banks and etc.?
In cases of that with respect to IT farms, etc., certainly harmonic filters are they're necessary. As you saw in the earlier slide, what the effects of having conventional capacitors. Utilities won't be reducing their capacitor switching in the near future. It actually, as I said, we do a lot of harmonic analysis and power monitoring for years, and certainly we see way more utility capacitor switching now than we did 5, 10 years ago. And that's simply because the load, has been increasing. The transmission reliability has been decreasing in some cases, only because we have some transmission lines and local distribution feeders are more heavily loaded than before. The one thing that I would say that in most IT farms, large computer, typically the power factor is fairly high, and power factor is not even required. Even typically a computer even is generally around the unity. The only thing that actually reduces the power factor would be the air conditioning loads on that, and that sometimes could warrant putting in power factor correction if the savings were there. but always would be recommending a harmonic filtered bank or any kind of loads that have sensitive equipment. And this is now even getting into CNC machines, etc. That's it.
Thank you.
Does that answer the question?
We'll have to get a response back from Paul. If Paul, you can just confirm that was answered for you. In the meantime, if there's anyone else who has a question, you can raise your hand within the control panel at the very top. It's a vertical bar, or you can just type them within the in the chat section below, and we'll get that question out. So yes, Paul said that was okay, that your answer was sufficient. So thank you again for joining us, Don, and thank you to all the registrants as well, and thank you for being patient with us with this new technology. The recorded version of this webinar will be posted online, and I will be sending out a link to that very shortly. And if you have any questions, you can always email me at any time or call me at 416-661-6600, extension 5569. Thanks again, and have a great afternoon.
Good afternoon, everybody.